Alright, here's a quick tutorial on how to add pathfinding to your flocking system. And we're done. Okay, let's make this for real now. This video is a continuation of this video, so yeah, now you know. This is a hint to go watch it if you haven't. Okay, game plan. The boys must be able to move around this wall to their destination. Now I know that sounds crazy for your average Roblox code, but stay with me now. Bro, what am I fucking watching? It's 3.7 million peak, by the way. Anyways, this video will actually be the first of 3 videos or more. I can't really know for sure. Why do I need to divide this into 3 videos? Well, because at first I thought, pathfinding for voids, easy. I can just implement the pathfinding service into our current void system, make the video, and call it a day. Right? Right? No, it was not that simple. So first I made this leader-based pathfinding system, but then... what the f... I can't teach this system to my viewers. I would get an endless stream of comments from script kiddies telling me, "Oh, it doesn't work, creator. Can you help me fix my code? Instead of me fixing my own code?" Or I would get comments like, "Line 102 of the code doesn't work." Also, I know what you did to Lysandra Woods in that alley. That's weird. So now I will be teaching you all about Flowfield pathfinding. It's a great pathfinding method found in many popular games, and it's also the perfect method for our little voids over here. So first, we need to generate a Flowfield. But what on earth is that? Well, it looks something like this. As you can see, it's a grid filled with cells. Each cell has an arrow, but these arrows won't be shown in-game. These arrows represent the pushing vector force in their respective cell. If it points down, then whatever thing in that cell gets pushed down. You get the idea. And as you can see, the destination is here. So if you just pick a point and then follow along the arrows from anywhere on the flow field, you will eventually end up at the destination, aka pathfinding. Yeah, that's the whole point of the video. Yippee. The reason this is so good for voids is because every time that we decide a destination, we only need to compute the flow field once, and then every void can follow it. This means that it doesn't matter how many voids you have. The performance stays mostly the same since they're all following the same generated map. There is one downside to flow fields though. You need to build your obstacles in grid increments, which can limit how you place things. Now you could increase the resolution of the flow field like so, but higher resolution will mean more memory usage, so keep that in mind. Okay, so now we have a plan. Let's get started. I'm gonna continue with the same project from last time, so you know where to pick off. Let's create a new folder called Flowfield Generation so we don't get confused, and insert a new module script. Call both this module script and its module Flowfield. Now let's write the functions that we know we will need. Well, I know, but you know whatever. First, our game will probably have a lot of different flocks. So let's make Flowfields replicable. We'll assign a new constructor and a generate function. Then make Flowfields an object-oriented programming class. Now we need a grid. Oh god, I did not miss this. So under the Flowfield module, I will make a grid module. And this will also be an OOP class. So Yay! Now, if your game has multiple areas, you can use this new constructor to create a grid for each area. But since for this test, we will only be in one controlled environment, so let's make only one grid represented by this variable. Now, how do we represent a grid? We'll do it with a table with indexes, and each index corresponds to a specific cell, like this. Each cell will be a nested table and recursively reference their respective neighbor cell tables. That sounds confusing, but you'll see what that means later. Since we only have one grid for this little project, things will be infinitely easier. We'll start by defining this imaginary grid in the world space. For example, how many rows and columns does it have? And how big are the cells inside the world? We'll store these as local variables. For now, each cell will be 4 times 4 studs big, and we'll have 10 rows and 10 columns. To continue, let's add an add walls function. So we can, well, add walls.
Yeah, no Sherlock!
Now, let's populate this grid. We'll put two for loops together like this, one for x and one for y. They both need to start iterating at 0, and then until height or width minus 1. Then we'll calculate the indexes with this, and then make this new table the value. Visualizing it, the table should look something like this now. After this, we can wire in the neighbor cells. So let's loop through the entire grid again and put each cell's neighbor inside themselves, called up, down, left, and right. Now don't worry too much about what direction a row or column goes. We are in a 3D space. I don't know either. For up and down, it's simple, just plus and minus the width of the grid. However, for left and right, it is not as easy. Due to the stupid but performant way we index the grid, modulus arithmetic starts gaslighting you. This is easier to show than to say, so here's a quick little graphic. As you can see, the cell at index 11 would say that index 10 is the cell on its left, right? Because left and right is just minus 1 and plus 1 the index. But as you can clearly see, it's not there. So where is it? Son of a... This problem also applies to the cells on the right edge. So we'll have to add these two checks to essentially fix our problem. If you want to understand what this piece of conditional code does, search up the modulus operator. And yep, I think that's our grid system done. Now pat yourselves on the back and get yourselves perhaps a nice cup of tea. Okay, let's get back to work. Just so we can see it visually in the workspace, let's add a block for each cell we made. Now let's get started on our actual Flowfield module. We'll require the grid inside the module to get the grid table we just made. Now for each Flowfield object, we will have a cost table and a flow vectors table. Costs are basically how far away a cell is from the destination. For example, this cell would have a cost of 5. As you can see, 1, 2, 3, 4, 5. And the flow vectors will be the vector force of each cell, as mentioned before. The way that we will know what costs and vectors belong to what cell is that the indexes inside these tables will basically be the same as the indexes of the cells in the grid table. Now it's time for the actual Flowfield generation logic. Basically, this generate function should and will calculate the cost and vector of every cell in the grid based on what the destination cell passed in is. After this whole function runs, we should have successfully made a flow field. First, let's clear out everything from a previous generation of costs and vectors from these tables in our flow field object. And now we need a breadth first search algorithm. Basically, it looks something like this. And what it essentially does is spread out, then calculate how far away each cell is from the destination cell, aka their cost. To explain it step by step, it first picks a cell and calculates its cost. Then it further calculates the cost of that cell's 4 adjacent neighbors, which is basically just the root cell's cost plus 1. The neighbors will then be added to some sort of queue, which they will become root cells in later calculations. And this whole thing keeps on looping and looping until the entire grid's cost is calculated. So now let's translate all of that into code. God, that was so hard to explain. First, we need a queue. Now from the name itself, you could kinda already tell what it is, but for context in programming, a queue data structure basically states that the first data that goes in is the first data that comes out. Because that's how queues work in general. If you're in a canteen and you queue up for the food first, you get the food first. Yeah, that's like a queue. Anyways, to replicate a queue in Roblox Luau, we can use tables. I will just quickly make a new module script, and this will be another OOP class for making queues. Queue.new makes a new queue, and then we will have these functions. Quick rundown. And queue adds a value to the queue. DQ removes the earliest value in the queue because it's a queue. Also, it returns the removed value. GetSize just gets the size of the queue because why not? No, but actually we use it later on. Go back to the flow field and store a new queue object in a variable. And now we have an official queue. Goddamn, how many times did I say queue? Now we write a repeat loop until the queue size is 0. Also, this loop is nice because if it never ends, then you will have just successfully invented a lag machine. Good job. Oh yeah, also forget to mention, with this new function we wrote, we can pass in a table. And this will serve as the table in which the queue works. And we also need to pre-add the destination cell into it. Don't forget to add the destination cell to the queue. If you did forget, congratulations, your loop just doesn't run. Good job. We also need to state that the cost of the destination cell is 0. Now inside the repeat loop, we first get the cell at the front of the queue by dequeuing it like this, then set the next cell cost to be the cost of the front cell plus 1. If you remember, we set each cell in the grid to contain their neighbors, up, down, left, and right. So now, we check through all the neighbors, state their costs in the cost table, and then add them to the processing queue. And yeah, that's actually the entire BFS algorithm. This loop should now set the cost of every cell correctly. And if you can remember, we made a block to represent each cell in the workspace and set their names to their respective indexes. We can actually visualize our BFS algorithm in real time. So let's turn neighbors yellow like this, and then we can turn the front tile green like this. I further made this normal script, and this is what's going to require and activate the modules. Let's require the flow field module and get the grid table. And we can just store the flow field in this variable. We use cell 40 in the grid here as the destination cell to generate to. And yeah, let's run the game. Okay, our loop here is actually so fast that everything just turns green immediately. So let me just nerf it real quick. Look at that, it works. Crazy, right? It almost brings a tear to my eye. If it doesn't work for you, a good chance is you made a teeny weeny little typo in your code. So this is to say that before you come into my comment section whining about it not working, please check your fucking code. Alright, now on to the next step. Assigning vector forces to the cells. This step is just super simple. We loop through our newly populated cost table and then do a nested for loop that iterates through all the neighbor indexes of that cell. We haven't wrote this function yet, so let's scroll up and define it. This function will identify what indexes the neighbors of this given cell index has, then return a table, with 1 being the up cell, 2 being the down cell, 3 being left, and 4 being right. Okay, this should work now. So let's scroll back down, and now we are iterating through a table of neighbor indexes. Now, for any of the neighbors, if the root cell's cost minus the neighbor cell's cost is 1, then we can set the vector of that root cell to point toward that neighbor and then break out of the loop. Since a difference of 1 automatically means that that neighbor cell is the closest one to the destination. As you can see, I have defined another function called toVectorFlow. This function shall take in the current index of the neighbor table and then convert it into the correct up, down, left, or right vector in the world space. Let's scroll up yet again and write it. Now I already did the trial and error, and I of 1, which is up, is negative z-axis in the vector tree, and then the rest is, yeah, that. It correlates correctly. I checked. So yep, we've now actually completed the entire field generation code. Awesome. Like and subscribe for more. See you guys next time. Oh, what? You want to actually see the arrows? God damn it, fine. Let me just grab a few directional arrows from the toolbox and assign them correctly in the loop. And now, ladies and gentlemen, enjoy Flowfield ASMR. Yeah, that was a cool montage and all, but can I please end the video now? Okay, so all this is useless if we don't have any obstacles anyway. So let's finish our addWalls function. You'd think all we have to do is set the index of the cell to the grid to nil, but that's only part of the equation. We also have to remove all references of the original table in the neighbor tables, because it still lingers there. And neighbors of the removed cell will still think it's there. Okay, now we should have done everything for this video. Oh my god. Now let's add some walls like this and see this thing run back in action for the final time. Alright, next time we'll add voids into the mix and see how we can use these generated flow fields alongside it. So thank you everyone for watching, and I'll see you next time. Phew. Okay, now where do I hide this body?